In this video, we're going to look at autonomous equations and the phase lines that go with them. We're going to find equilibrium values for autonomous first-order differential equations. We're going to determine if the equilibrium values are stable, semi-stable, or unstable. And we're going to draw phase lines and bifurcation diagrams. So using a sign chart, sketch this graph. Now, the sign chart goes back to pre-calculus 1, and I would have said, okay, I'm going to put x and then x minus 2 because these are the factors. And my places of interest was when x is equal to 0 and when x is equal to 2. And all I did was set each one of the factors equal to 0. In this interval from 0 to 2, we have an interval from 2 to infinity, and we have this interval from negative infinity to 0. And what the sign chart does is it tells us whether or not we are above or below the x-axis. So if I choose a value in this interval between negative infinity to 0, say I choose negative 1, this will produce a negative number. This will produce a negative number. That means this region is positive or above the x-axis. If I choose a number in this interval, say 1, I'm going to get a positive 1. I'm going to get a negative 1. This region is negative, and that tells me that we are below the x-axis. And then my last interval, I'm going to choose something in 2 to infinity. So I'm going to choose, say, maybe 100. This is positive, this is positive, this is positive. So that region is above the x-axis. So I'm going to come over here, and I know at 0 and at 2, I am below, above, and above. And so the graph is going to look something like this. Now, this is just a quick sketch. If I wanted to know exactly what the graph would look like, I would find some more points or maybe use calculus to figure out where my vertex is and all of that stuff. But that's not what we're doing. We're just using a sign chart to give us an idea of what the sketch of the graph would look like. There's going to be a reason why I do this. Now, we're going to define what an autonomous first-order differential equation is. It is x prime is equal to a function of t and x. You might also see this as y prime is a function of x and y. Just depends on which book you open. These are differential equations in which the slope function depends only on the dependent, which is either x if I have it as x prime, or y if I have it as y prime, and not explicitly on my independent, whether it is t or x. So in other words, the rate of change of x does not depend on time. And they can be wrote in this form: x prime of t is equal to dx dt, which is equal to f of x. Another way you may see this is we have y prime of x is equal to dy dx, which is a function of y. I know we keep moving from x's and t's and y's and x's and y's. It's just because it just depends on the book and or the sources for the homework. So we want to be able to be fluid with it. Now we need to determine whether or not the ordinary differential equation is an autonomous differential equation. So you might see ADE, which means that we are talking about an autonomous differential equation, whereas ODE is ordinary differential equation. We take a look at these and we're trying to decide whether or not I see a dependent only or a dependent with independent. Now we can see that A has both the dependent, which is the x, and the independent, which is the y. So this one is not. So this one is no. Now this one, the dependent is y, the independent is x. This is only a function of y, so the answer is yes on this one. This dependent is y, my independent is x. This is a mix of both, so this one is no. So just being able to classify what it is going to help us as we move along. Now, autonomous first-order differential equations, ADE, are always separable, and the solutions have very limited types of behavior. The constant function, where I have x of t is equal to some constant, such as f of r is equal to 0, is called the equilibrium solution of the autonomous x prime of t dx dt is equal to f of x. Since the slopes only depend on my dependent, which is x, or y if I have it as a function of y, as a slope field as defined in our previous section 2.2 for an autonomous equation is completely determined once the slopes along any vertical line t is equal to t bar are plotted. So in other words, all I really have to do is find my values along my axes, that is the dependent axes, and everything else will be copied left to right. If f of x is defined and continuous for all x, the behavior solutions can be condensed to just the slope of the lines along your dependent axis. In this case, if my dependent is x, then it would be the x-axis, which would be vertical. If I'm talking about the dependent being y, it would be the y-axis, which is vertical. And we call these a phase line. When we're looking at the phase lines, we find that we have sink, source, and node. So what a sink is when my slope field, when I do my slope field on only my vertical axes, is pointing toward it from both sides. It's a source if I have one, they're pointing away from both sides. So in other words, they're both pointing away in this graph right here. We see this as a source. And then a node is when it is pointing, one is pointing toward and the other one is pointing also, so one is pointing away and the other one is pointing toward. That's a node. And then we say that a sink is stable, a source is unstable, and a node is semi-stable. So if we look at this graph, I have y multiplied by y minus 2. This is what the slope field looks like. And you can see that along the y-axis, which is my dependent, that whatever's happening on my y-axis is copied and pasted both the left and right side of my y-axis. Because this is true, I can just draw a phase line and it will represent this entire slope field. Now, if you're trying to figure out why did we have this warm-up? Well, if I look at my warm-up and I graph y minus 2 on the y-axis, so I'm going to cross right there, and at 2, which is right there, I would have a graph that looks something like this. And you can see in this region is where I'd be to the left of the y-axis, and this region is where I'd be to the right of the y-axis. And you can see that in this region, all my slopes are positive. This region, all my slopes are negative, and in this region, all my slopes are positive. So in other words, I'm just trying to figure out where my slopes would be positive and negative. I can also do by plotting points along the y-axis to kind of, or not points, but slopes along the y-axis to kind of get a figure of what these would look like, kind of get an idea of what it looks like. Now you can see that this is positive and this is negative. My slopes are pointing toward, so it's a sink, which means it is stable. And these slopes are pointing away, so it's a source, which means it is unstable. Now, if my dx dt equals f of x satisfies the conditions of uniqueness theorem that we have in 2.1, then the solutions of all ADE, which is autonomous differential equations, must remain bounded between two equilibrium values, since they are solutions and solutions cannot intersect. So to draw a phase line, basically what you want to do is you want to determine whether or not you have an autonomous differential equation. And I would recommend that you just factor and graph it along the vertical axis as if it was a regular x-axis along the horizontal, and do the plus and minus. And then from there, you can draw your phase line. So I can see on my graph right here at x equals 4, so here's my phase line. At x equals 4, it looks like they're coming toward it. So it looks like I'm coming in like this, and I'm coming in like this. And it also looks like at 0, looks like these are pointing away, and these are pointing away. So I'd be pointing away, and I'd be pointing away. So this is a sink, which means we are stable. This is a source, which means we are unstable. Now, if I'm not certain how to graph this, of course, what I can do is I can turn my paper sideways, and I can see I'm crossing at 0 and I'm crossing at 4. And so I would have actually a graph that kind of looks like this, where this region is a negative, this is positive, and this is negative, if I were to do a sign chart for that. So looking at this without doing anything else, I know that this region would represent positive, this region would represent negative, negative, positive. I also see that something's happening at 3, something's happening at 1 and something's happening at -1. So here at -1, here at +1, here at 3. Now these would be positive slopes, so they'd be something like this. These would be negative slopes, so it'd be something like that. And then we have positive slopes in this region, and then we have negative slopes in this region. Now, this is just giving me, these are going in the wrong direction. These should be negative slopes. This is just going to help me decide. These are obviously not drawn to scale, and they're not drawn well. They're just going to help me decide which way my arrows are going. So you can see that these are positive, so I'm going to be going in this direction when I'm above 3. From 3 to 1, my arrows would be going in this direction, would be going down. From 1 to -1, we have positive slope, so it's going to be pointed in this direction. And then below -1, it's going to be pointed in this direction. So positive translates to my arrows going up. Negative translates to my arrows going down. So this is a source, which means just unstable. This is a sink, which means we are stable. And this is a source, which means we are unstable. Now let's take a look at C. So once again with C, my y is pointing up, and this factors into y -1, y +1. So I have right here at 1 and right here at -1. If I were to graph it, it would look something like this. So this represents positive slopes. So these are negative slopes, these are positive slopes. So positive would look like this, negative would look like this, and positive would look like this. The phase diagram then at 1 and, or phase line, excuse me, then my phase line at 1 and -1, positive means I'm going to move away from my equilibrium point. Negative means, in this case, I'm going to be moving away from and toward 1, so away from the 1 and toward the -1. And then, of course, I have this. So you can see, for this, I have a source here and a sink here. At y is equal to 1, I have a source. At y is equal to -1, I have a sink. Let's take a look at my next example here. We can see, let me erase this so I can see this a little bit better. Now, this is my x-axis, and this must be my t-axis, My first one is going to be at -1 and 1. That's what this one graphs to, is -1 and 1. And then I have at -2. So here's at -2. Everything we learned in pre-calculus 1 in terms of zeros and bouncing and touching and crossing are still going to hold true. If you're not certain, you can always do a sign chart. And so your sign chart would look something like this. You'd have x -1, x +1, x +2, the quantity squared, and you would figure out where you are above and below. Now, this x -1 becomes x -1, x +1. Its multiplicity is going to be a passing. This is x +2, the quantity squared. Its multiplicity is tells me that I'm going to touch and bounce off, because it's a multiplicity of 2. Again, this is pre-calculus 1 refresher. So if I know I'm going to touch and bounce, all I have to really do, if I don't want to go through a full-blown sign chart, is just put in 0 and see whether or not I'm positive or negative. And if I put in 0, I'm negative. So it's going to look like this. It's going to come in, come over, touch, bounce, come back off. So that's what that graph would look like. Negative slopes in this region, positive slopes in this region, positive slopes in this region, positive slopes in this region, because I am positive, negative, positive, positive. My phase line, I have something going on at 1, something going on at -1, and I have something going on at -2. Positive slopes, in this case, I'm going to be pointing up. Negative slopes means I'm going to be pointing down to my next equilibrium. Positive is pointing up, positive is pointing up. So this is the first time we see a node. So right here we have a node, which means we are semi-stable. Here we have a sink, which means we're stable, and here we have a source, which means we are unstable. Last thing we're going to talk about is bifurcation in equations with parameters. If it's an autonomous differential equation which contains some parameter, we're going to call it alpha. So that x prime is a function of my dependent and alpha only, still does not have my independent. The phase line will change as alpha varies. As my parameter varies, my phase line should change. So a smooth change, a small smooth change with my parameter causes a sudden quantitative change in the behavior of the solutions of differential equations. Then we say this is a bifurcation has occurred. The value of the parameter at which it changes is called the bifurcation value of the parameter. So let's go to look at our logistic growth models. And in particular, we're going to look at the logistic model with harvesting. So let us think about a pond with trout in it. It has a carrying capacity of 200 fish, and it can be modeled like this. So we talked a little about this in my previous videos about the logistic growth models. So N is the carrying capacity, H is the harvesting parameter, and K is the growth model. So if we allow 32 fish per year to be harvested, then you can see that P, again, is still the same as up here. 1 minus P over 200, still the same, but now I'm harvesting 32 fish. This is my alpha. This alpha is 32 fish, which is being harvested. And you can see when I go to graph this, I have a equilibrium position right here when we're about 160. And then we have another one which is at 40. Now, at 160, if I start out with 200 fish to begin with, or above 160 fish, anytime I have above 160 fish, then eventually it's going to get down to 160 fish over time. If I have between over 40 and 160 fish, it will also come up and reach 160 fish. This is a sink. This is a nice stable equilibrium. If I started out with less than 40 fish, then when I start harvesting 32 fish per year, the number of fish in the pond eventually will go to 0. So you can see this is a source, which means it is unstable. This equilibrium point is unstable. I have to have more than 40 fish. If I have less than 40 fish, all of the fish are going to eventually die out. Now, this next one is with 50 fish. So let's do this with 50 fish. Let's see what it ends up happening. Again, same exact formula, except for now my alpha is 50 fish. My equilibrium point is right here at 100. If I have more than 100 fish, then eventually, if I allow 50 fish a year to be fished out, it'll eventually equalize down to about 100 fish at any given time. However, if I have less than 100 fish to begin with, if I continue to allow 50 fish a year to be harvested, eventually there will be no fish in my pond. Lastly, if I decide to harvest 100 fish in this pond, there is no equilibrium point, and what will happen here is that eventually we will fish them all out. I just wanted to say, I wanted to talk about this back up here. When we had P is equal to 100, that was my equilibrium point, and this was a node. It was semi-stable. It wasn't stable, it was semi-stable. So anything below will fish us out, anything above will equalize, but it's not stable, it's semi-stable. Whereas this one, there is no equilibrium point, and we've just fished out the entire pond, which means we're now out of fish. So to better understand what we're looking at, let's go ahead and take our function of the h of p, which is dp dt, which is then going to be rp 1 minus p over n minus h. If we find the equilibrium solutions, we'd set this thing equal to 0 and we would solve. Using the quadratic, I have n over 2 plus or minus the square root of n squared over 4 minus hn over r. If this is less than 0, there's no equilibrium solutions as t gets really large. That was an case in which I had 100, and of course we got too large. If this is greater than 0, then we get a sink, and when we have P1, we get n over 2, which we know is a sink. And then we have the second solution, which means that P is a source. That was my unstable and my stable. If it equals 0, this is when we have one solution. So this was when we had this is when we had 100 fish that we were fishing. This is when we had 50 fish that we were fishing. 32 fish we were fishing. 32 fish that we were fishing, and this is when we had 50 fish, which we were fishing. And you can see that the small change had dramatic effects on how the equation behaved. If I just change the H value and the amount that I'm going to harvest from 50 to 50.1, we're going to doom the population of the fish to extinction no matter how big the initial population was, whether up to 100, because that's a carrying capacity. So whether I started out with 199 fish or I started out with 52 fish, if as soon as I have 50.1 fish, obviously you can't have 0.1 of a fish, then I have just doomed my population. So here is when H is less than H star, and H star is the bifurcation. The bifurcation in our case, which was 50. So when we had H less than 50, the harvesting amount was less than that 50. We had this. When it equals 50, we had this. And if it was greater than 50, we had this. The bifurcation value of the harvesting parameter is called the critical harvesting rate. And if I do a collection of phase lines based on my H's, so here's my collection. This is when H is less than our H star, when H is equal to, and when H is greater than. We connect these by using a solid line if we're talking about a sink, and dotted lines if we're talking about a source. So this is what it would look like in this region. We're going to have a sink all the way up until we hit this node, and our source, and then of course, is unstable. And notice how those are connected. And that's it for this video. So not too long, not too bad. And we'll talk about this in class. Hopefully you will all watch the video this time. I think I'm going to start putting random questions in, random notes of information in these videos, and then ask you it on the test, and that way I can tell whether or not you actually watch the videos. And I'm going to ask you about this, my rambling at the end of the video in class. That's it.